Welcome to EDU World Space.
Let's go to the next page here for some more room. So for part A, we have the Cantor set. This is where you take the closed interval 0 to 1, and then the first thing you do is you just remove the middle 1/3 here.
Here's a clean and professionally formatted
So
presentation
everything
of the calculation
between
shown in the image.
1/3, well, not
Application
including
of the work
1/3,
energy
and then
theorem,
here
wet. From the
we'll
work
pick up
energy
at
theorem, the
2/3 and
force
go back
F
to
is given
1.
by F equals
So
the frac text
removing this
KE,
open
where
middle third
KE
interval.
equals kinetic energy.
And then
S
the next step
stopping
is to
distance.
just do the same
I'm
thing,
given
but for
for
these
object
smaller
A,
intervals.
FA equals
So
frac
here,
100,000,
I'll take out the middle third.
For object B, FB equals frac
So I'm still at 0.
1500
And
for
then this time I
0.15
stop at a
times
third.
and force
That's a
ratio
ninth.
frac FA,
And then
FB
2
equals
ninths.
frac 0.10, 0.15
All the way
equals
back
frac
to
2
1
end
over
result.
3.
A box frac FA, FB.
And then over
Would
here,
you like a PDF
this
version
is
of
2
this
over 9,
explanation?
or you could think of it as 6 over 9. 2 over 3. So then we go one more over to 7 over 9. And then we take out between 7 over 9 and 8 over 9. And then you pick back up at 8 over 9 and go back to 1. So the same thing we did from the first row to the second, we also did it from second to third. And I would continue in this fashion, and it's going to be very hard to draw the next one, so I won't be able to label it. But we take out the middle 1/3 of each of these 4 lines, and basically I'll stop writing there because it's just becoming too hard to draw. Now I'd like to find the sum of removed lengths. Each step we remove the side length. Here we remove the third. And the first step, from step 0 to step 1, we took out a third. Then from this step to the third row, we didn't take out a third, we took out a third of a third. So we really took out a ninth, and then we did it twice. So that's 2 over 9. Or you could think of that as 2 over 3 squared to make this look like a geometric sum. And then going from the next line, we would take out a third of this ninth, but that would be 1 over 27. And then there's a total of 4 of them. There's one there, 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 and here as well. So that'll be 4 over 27. And we could write that as 2 squared over 3 cubed, and so on. So we see that this is a geometric series. And we see that our r, the thing that we're multiplying by each time, is 2/3. So we can go ahead and we have a sum formula for a geometric series. You take the first term of the whole series, and then you divide by 1 minus r. In this problem, the first term in the series is this 1 over 3. And then we divide by 1 minus 2/3, but that's just a third over a third, and that equals 1. And that's exactly what we intended to prove for part A. Now let's go ahead to the next page for part B. This time we are looking at the Sierpinski carpet. So you start with the square of side length 1, and then we come inside the square here. So let's maybe look at this middle 1/9. We want to remove, think of the square as this big square. You could break it up into 9 pieces. We'd like to remove this middle square here. And then eventually, and we like to continue this pattern. After I remove the square, then I'll go inside of each of these 8 remaining squares, and then I'll also go inside there and also remove the middle 1/9. So we have 8 left. We had 9, and then we took out a square, and so we have 9 little ones. So removed area, we would like to add that up and show that it's equal to 1. Well, from the first square, the removed area, you just remove the 1/9 of the square. So 1/9, the whole square, the large square has area 1 times 1 equals 1. So 1/9 of the square, it has area 1/9. Then in the next step, let's go to a different color here. Let's go to blue. Now, after we zoom in on each of these squares here, now we're looking at squares of this size. They all have a little window. We'll go with that little 9th. We'll go in there and shade all those. So we're removing all of these areas here. And notice that there's 8 of them. So let's write that we have 8 of them. And then what's the area? Well, each of these squares has area 1/9. And then we're looking at 1/9 of the inside. So that's 1/9 squared. A 9th of a 9th. So this is 8/9 squared. Let me write that as 2 cubed. No, actually, let me write that as 8. 8/9 squared. Now the next step would be to rinse and repeat the same process. Now I go to one of these squares here. I go to one of these 8 squares. And then I go inside of that square. And then so let me do it over here on the left with the blue. Then I break this up into 9 pieces total. I've removed the middle piece, but then I still have these 8 remaining squares that are inside. So we can see where the 8's coming from. We always have 8 little windows left over. So there, I have 8 of these green windows, but each of them have 8 of their own smaller windows on the inside. So that's 2 8s. And then here, how many 9s? Well, we started off by taking a 9th. Then we took another 9th. So, and then here this is our third time. So this time we're actually doing 3 9s there, a 9th of a 9th of a 9th. So here, the third time we remove the area would have 8 squared over 9 cubed. And we could just see the pattern now. This is geometric. Geometric with r equals 8/9. This is what you're multiplying by each time. And we know the formula for a geometric series. You take the first term of the series, and then you just divide it by 1 minus r. In our case, the first term is just 1/9. We could see that up here. That was the first step. And then we do 1 minus 8/9, because that is our value of r. Go ahead and simplify that. You get 1/9 over 1/9. That's equal to 1. And that is precisely the sum that we wanted for A and also for part B. So this is our final answer.